Welcome back. Today we're going to tackle one of the most powerful, and often intimidating, concepts in linear algebra: eigenvectors and eigenvalues. My goal is to give you a simple, visual intuition for what they are and why they are so important for AI. To understand eigenvectors, we first need to remember what a matrix does. A matrix is a transformation. It can take a vector, or a whole space of data, and stretch, shrink, or rotate it. Imagine a gust of wind blowing across a field of arrows. The wind is the matrix, and it transforms all the arrows, pointing them in new directions. Now, in that field, there might be a few special arrows that were already pointing in the same direction as the wind. When the wind blows, these arrows don't change the direction at all. They just get stretched out or maybe shrunk down a bit. These special, unwavering vectors are the eigenvectors. They are the characteristic directions of the transformation. So if the eigenvector is the special direction, what is the eigenvalue? The eigenvalue is simply the number that tells us how much that eigenvector was stretched or shrunk. It's the scaling factor. A large eigenvalue means that this is a very important direction for the transformation, one where things are stretched a lot. A small eigenvalue means it's a direction of shrinking. This is incredibly useful in AI because it lets us find the fundamental structure of our data. For a high-dimensional dataset, the eigenvectors point in the directions of highest variance, where the data is most spread out. And the eigenvalues tell us how spread out the data is in each of those directions. They give us a ranked list of the data's most important axes. This idea is the engine behind some of the most famous algorithms in data science. The most popular technique for dimensionality reduction, principal component analysis or PCA, is nothing more than a process for finding the eigenvectors and eigenvalues of a dataset. And the original PageRank algorithm that built Google was based on finding the principal eigenvector of the massive matrix representing the entire internet. So, in short, eigenvectors and eigenvalues let us boil a complex dataset down to its essential structure. They find the hidden axes that define the data's shape, and they rank those axes by importance. It's a powerful way to find the signal in the noise. In our next lesson, we will see this in action as we do a visual walkthrough of principal component analysis.